My name is Clara Moge, and on behalf of my co-authors Youngjun and Katie Wang at University College London, I will be presenting our paper, Shared User Interfaces of Physiological Data, a systematic review of social biofeedback systems and contexts in HCI. Here, let me first talk about the basic pipeline of physiological computing, which has been explored in human-computer interaction contexts. Physiological computing, as an innovative approach to HCI, always starts with sensing human physiological signals like heart and breathing rate. This data is then processed, often with machine learning, to analyze and infer what psychophysiological states and emotions a user is experiencing. This physiological information is then used to generate an appropriate system response. This system adaptation works in a biocybernetic loop. The captured physiological information can also be sent back to the user for more direct interventions. This process is called biofeedback, where continuous physiological data is returned to a user in real time and in an easily understandable form. Biofeedback has long been explored to train individuals to control their physiology as a way of enhancing self-awareness and regulation. From here, our question arose. Provided that biofeedback can help users understand their own psychophysiology, can sharing biofeedback interpersonally help promote an understanding of others? And if so, what socio-emotional and well-being benefits can this bring? Although human physiology is inherently reactive to our social environment, for the most part, physiological signals do not constitute an explicit channel of information that humans use to interpret other people's emotional states. But with biofeedback, we're now at a stage where it's possible to externalize such data and see explicitly how others around us are feeling. Recent research into this rapidly emerging topic we call social biofeedback has suggested that as physiological information carries socio-emotional meaning, sharing biofeedback in itself constitutes a novel communication medium. Researchers have found this can be leveraged for collaboration, educational outcomes and social play, and even to enhance feelings of social closeness and intimacy, creating positive user experiences. To further explore the current landscape of social biofeedback technologies, we wanted to understand what types of interactions occur in physiological social space, and if biofeedback sharing is a communication medium, in what context does this communication currently take place and with whom? Secondly, beyond transitory user experiences, what kind of socio-emotional competencies can be practiced and/or developed by sharing displays of physiological data? To answer our research questions, we conducted a systematic review and meta-analysis. We identified and screened research articles following the PRISMA guidelines. We were interested in research papers which included at least one defined indirect physiological measure, involved human participants, and described an experiment, prototype, or a system involving a minimum of 2 interactional partners. After the application of further eligibility criteria, we assessed all papers for quality prior to data extraction. The number of studies on social biofeedback sharing has gradually increased, particularly since 2013. Our analysis revealed a range of applications for social biofeedback, the most common being social play, from virtual reality to tabletop and outdoor gameplay, as well as telesocial tools from nonverbal communication to instant messaging and video chatting. Most social biofeedback systems use cardiovascular metrics. There was a significant range in how physiological data is fed back to users. Biofeedback was mostly presented visually, but increasingly in more implicit ways, for example through avatars changing their characteristics as a function of physiological activity. Here we highlight some of our key findings, particularly from our analysis based on the time-space taxonomy of groupware, which categorizes interaction types into 4 dimensions, along with spatiality and temporality. Interestingly, our analysis shows the majority of current social biofeedback systems are designed for use in distributed contexts. Examples include telesocial tools like Nemo, which allow users to send mood representations derived from heart rate data via a smartwatch, or the Dynacom virtual environment for dyadic meditation based on respiration and EEG. In distributed contexts, social biofeedback is used for interpersonal connection and to enhance feelings of social presence. Most social biofeedback systems are also designed for use in synchronous time, which is particularly important for overcoming physical distance during social activities, from games to meditation and distributed exercise. In synchronous interactions that are either co-located and distributed, we found social biofeedback has more of an informational role. It is used to inform co-users of each other's real-time states in the context of a social task. Building on these findings, we began articulating the physiological-social interaction space. We identified 5 modes of interaction, which can be categorized according to symmetry. Here, with symmetry, we refer to interactions wherein physiological data is obtained from more than one user. Asymmetrical interactions essentially follow a participant-observer model. Here, we distinguish between interactions wherein users' physiological data is only accessed by a secondary user, and those in which both primary and secondary users have access. In contrast, symmetrical interactions are those in which co-users all have access to biofeedback. The differentiation here lies in the content of the biofeedback received, specifically whether co-users receive biofeedback from only their co-user, both their co-user and themselves, or whether they receive an aggregated measure of their combined physiology. This is all combined in the Social Biofeedback Interactions framework that we propose. This framework shows the basic physiological data flows in multi-user interactions around individual and collective physiological display interfaces. It also considers behavioral forms of feedback between users. Here we discuss 6 key socio-emotional benefits from social biofeedback interaction systems, which we have identified through thematic analysis. The first 2 are intrapersonal socio-emotional competences, which are aligned with the main intended outcomes of biofeedback. Most importantly, social biofeedback extends these benefits to the point where users can practice socio-emotional skills oriented towards others and towards tasks. Empathy arose from shared positive emotions and synchronization of physiological activity. Users were also able to accurately infer and try to understand causes for others' internal states. Users also acted compassionately, explicitly validating the thoughts and feelings of others and tailoring behavior to make another more comfortable. Thirdly, interacting with social biofeedback sparked new connections with strangers and encouraged emotional disclosure in close relations. Finally, when social biofeedback is used for information in task scenarios, this increases engagement, group effort, and performance. Ethical considerations and mitigations should guide future research in this area. The intimate nature of sharing biosignals can create privacy concerns, especially when users don't feel they have control over their own data. We suggest aggregating or abstracting data and affording user control where possible. We also found receiving continuous feedback can encourage too much checking up on one another. We need to consider the potential for attachment issues to develop. Finally, we need to examine how to measure changes in socio-emotional skills and test over time whether practice can lead to long-term skills development and well-being improvement. This is the end of our presentation. Please check out the paper for more details. Thank you for listening.